Section 36.5 Radical chain reactions. Radicals are chemical species that contain at least one unpaired electron. For example, if you break the OH bond of a water molecule, two radicals are formed, the hydrogen radical and the HO hydroxyl radical. Radicals are often highly reactive. Now let me give you an example of radical chain reactions. This is a thermal decomposition of ethane in the gas phase. This ethane is decomposed into ethylene and molecular hydrogen. Now let's look at the mechanism. The mechanism includes three steps: initiation, propagation, and termination. So let's look at initiation. So in this step, if the temperature is high enough, it's possible to break a carbon-carbon bond in this ethane molecule to form two methyl radicals. In this step, radicals are produced. Propagation. There are three possible elementary reactions in propagation. Over here, CH3 may attack this ethane to form methane and C2H5 radical. C2H5 radical may decompose into ethylene and H radical. The H radical may attack the ethane molecule to form C2H5 plus molecular hydrogen. So if you look at these three elementary reactions carefully, they have something in common. On the left-hand side, you have one radical. On the left-hand side, you have one radical. On the right-hand side, you also have one radical. It's just you convert one radical to a different radical, from one radical to a different one, from one radical to a different one. Finally, termination, you'll see in this termination step, the number of radicals is reduced. So that's the three reactions. Because radicals are highly reactive, we can make steady state approximations to this 1, 2, 3 radicals. Again, we assume the change of the concentrations of these radicals with time is 0. And then we need to write out the expression for these three derivatives by looking at 1, 2, 3, 4, 5, the 5 elementary steps. For example, if we are looking at this differential equation, dCH3 over dt, we'll have to realize that this CH3 is produced in this reaction, it's consumed in this reaction. So in this case, we're going to say, well, the production rate of the methyl radical is K1 times the concentration of ethane times 2. The consumption rate of the CH3 is K2 times the concentration of ethane times the concentration of CH3 dot radical. And then we know 2 times K1 times ethane is equal to K2 times ethane times CH3 radical. So by doing so, we will be able to obtain the expression for this methyl radical right here. We can also obtain the expression for the hydrogen radical and this C2H5 ethyl radical. It's a little bit more complicated. It's a non-trivial derivation. Assume you're patient and careful, you will be able to get this expression for C2H5. The nice thing about this expression is however complicated this looks like, it's a constant. Now we assume K1 is much smaller than all other rate constant, this is reasonable. Because if you look at K1, in K1 you need to break a carbon-carbon bond. There's just only bond breaking. There's no bond formation. In these 3 steps, you have 1 bond breaking and 1 bond formation. Over here, you need to break a carbon-hydrogen bond, but then you form a carbon-hydrogen bond, right? And over here, although you break a carbon-hydrogen bond, you form a carbon-carbon pi bond. Over here, you break a carbon-hydrogen bond, and then you form a hydrogen-hydrogen bond. So, in these 3 steps, indeed, you need to break a bond, but also you form a bond. So over here, you form a bond without breaking any bond. So really, this step is the slowest step, because in this step, there's only bond breaking. There's no bond formation. Alright, in this case, we can further making changes. So we can neglect K1 if we're comparing K1 with some other species. We're looking at these 3 terms and realize this is proportional to K1, this is proportional to K1 squared, this is proportional to K1. This sum is raised to the power of half. So what we do is we compare these 2 terms and then we delete this term. This is K1 squared. K1 is really small, so K1 squared is negligible. So we delete this term. And then we compare this K1 to the power of 1/2 with K1 to the power 1. And then we can delete this term as well. So in the end, it's going to be just the square root of K1, K4 over K3, K5. So that's why we can write out this equation. And then we plug in this equation to the hydrogen radical expression. It's right here. And then we get the expression for the hydrogen radical. It's over here. All right. The resulting changing rate of C2H6 is thus this. C2H6 is involved in 1, 2, 3, 4 elementary reactions. This is the carbon-carbon bond breaking reaction of C2H6. I believe this is the reaction between C2H6 and the methyl radical. This is between ethane and the hydrogen radical. And this is the final termination reaction between these 2 radicals. Alright, so in the end, we just plug in all these expressions, and finally we get this expression for the changing rate of the concentration of ethane. So really, it's just a first order reaction, or pseudo first order reaction. And I would call this the effective rate constant for this pseudo first order reaction. We replace this with K effective, and then we can easily find the concentration of C2H6 as the initial concentration of C2H6 times e to the power of negative K effective T. Again, this is K effective. This is K effective.